Hi, this is cs517A, and for this video lecture I'm going to talk about process synchronization. OS ensures proper synchronization for the execution of processes that share resources, especially data. This is to maintain data consistency and integrity. During execution, the change made by one process may not be reflected when other processes access the same shared data, or it could be that the expected data have been lost because a process has already changed it during execution. To avoid these inconsistencies, processes have to be synchronized. So here is the process states. So when a process is being created, the state is new, and the process is waiting to be assigned to a processor. It becomes ready, and then when instructions are being executed, it's running. When a process is waiting for some event to occur, such as an I/O completion or reception of a signal, it's waiting. And when the process has finished execution, the, the state is terminated. So here is the graphical representation for the process states. You will see a lot of this graphical representation when you talk about CPU scheduling or even operating system. Let's look at the process state more closely. So you said that when a process is created, it becomes uh, new, or the state is new. And then when the CPU admits a process, it becomes ready. So normally, the new and ready states are where most of the processes are during the process state. So there's so many processes there in the new. It's either they're either in the new or in the ready state. Anyway, so after ready, when the scheduler said that okay state or okay process A, you will now go to the CPU. The CPU will now execute or will run. So it will pass through running. When a process is running, there are two, uh, actually three. So it can go back to ready, it could go to waiting, or it could be terminated if it has already been completed. So when an interrupt occurs or something would like to get the attention of the CPU, that process has to be returned to the ready state. So an interrupt happens, say for example, you remember your assembly language and you use those interrupt int. The most famous is interrupt 21, and you have so many function calls in AH. Anyway, so the point is there are some processes that could interrupt existing processes, and there are some processes that has higher priority than other processes. So whenever an interrupt is invoked, especially higher level interrupts, so whatever process is running, it has to be removed there, put it in the ready state, because somebody else powerful is asking for the CPU's time. So there's an interruption. Okay. So a process can also go to waiting state. So what happens? An example here is, for example, you're running a program and you have a menu program. So a menu that will require some interaction or intervention from the user. For example, you ask your user to enter yes or no, or click a certain button for yes or no. So when that happens, a process has to wait for an I/O or some other event. It has to wait. In the case of the menu program, it has to wait for a click before it could proceed. And we know that I/O devices are much lower than CPU. So the CPU will not waste time waiting for that I/O device. So instead, the process will be placed in the waiting state. So once the user completed that menu, we'll go back to that menu program. Once the user completed what is required for him to click or to choose whatever in the menu, then the I/O event has been completed. The process will go again to the ready state. So already said that once the process finished executing, then it It will go to exit and be terminated. Okay. But a process, normally process and threads, they will encounter a lot of challenges along the way before they will be completed. So two of those challenges are in the form of race condition and critical section problem. So race condition occurs when two threads access a shared variable at the same time. The first thread reads the variable and the second thread reads the same value from the variable. Okay, we'll have example of that later on. A critical section is part of a program which tries to access shared resources. The critical section cannot be executed by more than one process at the same time. Operating system faces the difficulties in allowing and disallowing the processes from entering the critical section. Critical section is the part of the program which tries to access shared resources. So here is an example of a race condition. So examine the following example to see how a race condition occurs. There are two threads and both are updating a shared variable called total, which is represented by double word pointer ds, and then you have this memory location in hex in the assembly code. So this is the Visual Basic Code, and these are the equivalent assembly code. So as you can see, this is straightforward assembly language. So you move, basically you just put the value which is total here, this is total, this is pointed by this value to your register EAX, and then you add EAX with your value 1, and then jump not what's O overflow, yeah, jump not overflow. So it just means that the addition has been successful, there is no overflow in the register. And then you clear EAX, because whenever you add, there are some value in EAX that happens and you need EAX. And then you call some piece of code in preparation for saving the result again to your original memory location, which is total. So same thing happens here, the only difference is R, the number 2, instead of add you have subtract, and then this call function. Okay, now here's the scenario. So total is 100, value 1 is 50, and value 2 is 15. Thread 1 gets an opportunity to execute but only completes step 1 to 3. So accordingly, hanggang dito lang tapos 1 through 3. So he was not able to save the value, the total value, although the value is still in the register, but it's not saved in the memory in your RAM. This is represented by your memory location in the RAM. Okay, this means that thread 1 read the variable and completed the addition. Thread 1 is now just waiting to write out its new value of 150. Supposedly put the value here 150. After thread 1 is stopped, thread 2 gets to execute completely. So thread 2 completed its execution. This means that it has written the value that it calculated, 85, out of the variable total. So this one, which is being shared here, the total is 85 now. Okay. Finally, thread 1 regains control and finishes execution. It writes out its value, which is 150. Therefore, when thread 1 is finished, the value of total is now 150 instead of 85. So here, you see, because thread 1 was stopped for whatever reason, so it was not able to put the value of 150 first. And then when thread 2 was executed completely, it puts the value, instead of getting the value of 85, we're assuming that the logical order here is thread 1 first will execute and then thread 2. right? So that the final value supposedly is 85, but in this case, because thread 1 was stopped before it has completed this execution, and thread 2 was executed completely, the value, because they are sharing the same memory location, has been compromised. This error is random because it is possible, of course, it's always possible for thread 1 to complete its execution before its time on the processor expires. And then thread 2 can begin its execution. If these events occur, the problem does not occur. So no problem. Thread execution is non-deterministic. Therefore, you cannot control the time or order of execution. Also note that the threads may execute differently in runtime versus debug mode. Also, you can see that if you execute each thread in series, the error does not occur. If it's in series, thread 1 first and then thread 2. This randomness makes this error much harder to track down and debug. To prevent the race condition from occurring, you can lock shared variables so that only one thread at a time has access to the shared variable. Do this sparingly, because if a variable is locked in thread 1 and thread 2 also needs the variable, thread 2's execution stops while thread 2 waits for thread 1 to release the variable. Okay, so that's race condition. Okay, so remember the critical section. It says here that it's part of the program which tries to access shared resources. The critical section cannot be executed by more than one process at the same time. That particular section. Okay, operating system faces difficulties allowing the processes from entering the critical section. Critical section is the part of a program which tries to access shared resources. Okay, so let's look at the two set of assembly code that we used previously for our race condition. So you will see here, which do you think is the, you might consider that this is the whole part, this is already the critical section, but if you are going to pinpoint here, pinpoint exactly where will be the critical section, where will it be? Or where will you stop the processor? Or if you're going to insert something there, a code, where will you stop it? Okay, so that's the critical. So before saving, because the upper portion is okay, it's still okay there, but here, this is the part. But if you want to extend, actually you can extend it to 4 for going down. But this is the part when the when the processor already will write the result to the memory location, because they are sharing the same memory location here. Okay. So a solution to the critical section problem must satisfy the following three conditions. These are the three conditions. First, mutual exclusion. Out of a group of cooperating processes, only one process can be in its critical section at a given point of time. Progress. If no progress is in critical section, and if one or more threads want to execute their critical section, then any one of these threads must be allowed to get into its critical section. Obviously, you still need to allow threads to go to their critical section, but there should be you should be absolutely sure, or that the CPU, the processor, should be absolutely sure, or the OS should be absolutely sure that there are no other processes that will go that critical section. Only one process. Bound waiting. After a process makes a request for getting into its critical section, there is a limit for how many other processes can get into their critical section. Therefore, this process's request is granted. So after the limit is reached, system must grant the process permission to get into its critical section. So there should be a waiting. There should be a certain time of waiting to allow other to get into their critical section. So Solution of critical section problems still. So one solution is synchronization using hardware. Many systems provide hardware support for critical section code. The critical section problems could be solved easily in a single processor environment. But nowadays, it's common to have one processor but multi-core, so it's already considered as multi-processor. Virtually, even though you have only one processor, but it's virtually multi-processor. Anyway, if we could disallow interrupts to occur while a shared variable or resource is being modified. In this manner, we could be sure that the current sequence of instructions should be allowed to execute in order without preemption. Unfortunately, this solution is not visible in a multi-processor environment. Although I would like to believe that this is still possible, but it will be very much harder, and it will be much more complex to do. If you're going to synchronize, you will use synchronization hardware with multi-processors setup. Anyway, disabling interrupt on a multi-processor environment can be time consuming. Here's the reason. As the message is passed to all the processors. This means transmission lag, delays, entry of threads into critical section, and the system efficiency decreases. Oh, of course, see, it's allowed, but the downside is it will slow down the processing power of your processor. So another solution is called the mutex lax. So as the synchronization hardware solution is not easy to implement for everyone, a strict software approach called mutex lax was introduced. In this approach, in the entry section of code, a lock is acquired over the critical resources modified and used inside critical section. And in the exit section, that lock is released. As the resource is locked to the process execute its critical section, hence no other process can access it. So you just put a mutex lock between, or sandwich that critical section with mutex locks. So very long. To recap, there is a need for a process synchronization to ensure consistency of data. A race condition occurs when two threads access the same variable. One thread reads the variable, the other writes in the same variable. A critical section is part of the program that tries to access shared resources. A race condition usually happens in a critical section. So for recommended further reading and viewing, please visit these sites. So thank you.